Okay, so here we have step 8 for the wind tunnel project, and our objective or process for number 8 is if the objects were dropped from a significant height, do the following. Part A, use the general form of the function from part 7 to create and solve an integral equation to determine the time to reach terminal velocity. B, using the general form to find, or from part 7, to create and solve an integral equation to determine the distance needed to reach terminal velocity. Part C, determine the terminal velocity for each profile. D, using the results from A and C, determine the time to reach 50%, 90%, and 99% of terminal velocity for each profile. And then part E, use the results from part B and C to determine the distance to reach 50, 90, and 99% of terminal velocity for each profile. So part 7 is referring to the functions that we discovered. So using the data given, which is the side of all of these, use the graphs in Excel, and we used or wanted to find a linear function of drag versus velocity. Even though we know it might not be the best thing, that's just the simplest form for this part right here. And we got a unique function for everything because drag is different on different objects, and as you can see in all the data at the same velocities, very different drag. So, and it's important to note, I would say that usually the force of drag is determined using the coefficient of drag right there, divided by 2 times air density times the area, surface area, times velocity squared. And so it's also important to note that in free fall, we're also looking at everything in that direction as positive in the downward direction. So we have the weight minus the force of drag going up, and velocity is going down. It's also accelerating downward. And so for every single equation here, our sum of forces is equal to the force of weight minus the force of drag. And moving on, we just use the force of drag. I just refer to it as F. And for terminal velocity, we know that acceleration is equal to 0. So this side goes to 0, and that means the force of weight must be equal to the force of drag. And that's how we can determine each part of each profile. But before we get to that point, we need to find an integral to relate time to velocity and also distance to velocity. First thing we are going to do is do the time component. And so here we know that mg minus fd, or the force of drag, is equal to m. It's important to note acceleration equals dv over dt. And basically, this side comes out to mg minus f equals m times dv over dt. This part here, a little complicated, but we can multiply by dt on this side, or on both sides, and divide by mg minus f. And so we get dt is equal to m divided by mg minus f times dv. Important to note, m is a constant for all of these, and so we can put m on the side, but taking the integral of both of these, we get t is equal to m times dv divided by mg minus f, or the force of drag. So that is the baseline for each equation. And then moving forward, for the distance, I refer to distance as x. In this case, it really should be y, because it's vertical, but just for, I just did x for comfort, I guess. But same thing, mg, sum of forces equals ma, forces equals ma, and then so mg minus f equals ma, and we know that acceleration can be is equal to dv over dt, which is also equal to dv over dx times dx over dt, which is equal to dv over dx times v, or velocity, which is, we have velocity in every single one of our functions. So they'll be related, but overall here, just working this out in my head, may have skipped a few steps, but just kind of seeing how this function is going to play out. But here we got, can divide by mg minus f, which is this, multiply dx out, and we get mv, or m, take it out of the constant, times the integral of v divided by mg minus f, which is over here. And yeah, so that is the integral that we'll be working with for every single the next functions or parts. So part A, we also have the mass of each object and such. I am going to explain in depth pretty much one of each integrals, because they end up all being very, very similar, and the execution, while they are different integrals, they all end up being very, very similar in the way that you integrate them and such. And so for me, I found a pattern. So pretty much just making sure we multiply that out and sub in our f for each function, the correct mass and such, and I use u substitution for every single one. U, for this case, u equals 0.341 minus 0.0046v, and we get dv is equal to negative du divided by 0.0046. And so what you find here is that dv is always going to be equal to negative du divided by the number in front of v, or as coefficient, you could say. And so doing u substitution, we get negative constant out front times the integral of du divided by u, which is equal to whatever out front, which is equal to negative 7.413 natural log of u. Important note that these are always absolute values, but we get negative 7.413 times the natural log of 0.341 minus 0.0046v plus c, because if you put v equals 0, so it's important to note also that at t of v, t of 0 is equal to 0, because when the velocity is 0, that means that the ball hasn't been dropped yet. So, or it hasn't actually started moving yet. So time hasn't started at that point. So that's a very important distinction. So we have to make sure that the function actually equals 0. And we use the plus c to determine that. And that goes for all of the integrals here. Later on, the same thing with distance. When the ball is equal, or the object is equal to, when the object's velocity is equal to 0, it hasn't started moving yet. So that was important for me, because when I put v equals 0 originally, I got that t was already a positive number, as if it had moved 5 seconds, which was just does not make sense. So moving forward, that is basically the same thing. I would like to note here we have mg minus f. You can see I highlighted each one here because we use those later on. Oh, this one. We use those later on to determine or just make things a little bit simpler. Here you can see here for part A, we'll go through part A for both, but highlighted both in green just to show where we kind of got that number from already, because in our pre-worked out, we have mg minus f in both. So we already have that calculated out, so might as well make it simpler. Yeah. So, yeah, moving forward. All of these integrate very similarly. We'll notice that we always have a constant c again to offput and make sure that we start t of 0 is equal to 0. But due to different constants, masses, stuff like that, and coefficients, we end up with slightly different numbers, which makes sense because none of the objects are the same. So basically, the process of finding the integral was the same for all, or finding t was the same for all objects. It was very simple, a simple pattern to see. And again, use substitution for all of them. And yeah, and then using our determined mg minus f values. Then this is going into part B, finding the distance, or using integrals to find distance. We have x equals m times the integral of v divided by mg minus f. And it's important to note that x of v, or it equals the distance, but x of 0 equals 0. So that's where the constant c's will be important to offset that and make that true. So here we use the same mg minus f from part A, but makes it a little bit complicated because we have a v up top and on the bottom. So use substitution again, but we can also do where u equals 0.341 minus 0.0046v, du equals negative 0.0046 dv, so dv equals du divided by negative 0.0046v, but since that's a constant, we can put that out front. But with the v up top here, we settle this here, so we can do a little bit of algebra, minus 0.341, and then divided by negative 0.0046. We get v equals u minus 0.341 divided by negative 0.0046, which we can put out front again. Negatives cancel each other out, and this is what we get for the next part. And then we can split things up. U divided by u is equal to 1, so we get this constant out front times just the integral of du, which is equal to u minus 0.341 du over u, which we know from the last one, which is the natural log of u, and still constant out front. And then resub in our u value, our u equals 0.341 minus 0.0046v, and we get x equals 594.532 minus 7.413v minus 594.532 times the natural log of 0.341 minus 0.0046v. It's also important to note, this value right here is what will determine, or actually also determines our terminal velocity, because this cannot be negative. We do have the absolute value from afterwards, but with normal brackets that can't be negative. I'm honestly not sure if I'm supposed to put it in normal brackets or not, but if we divided 0.341 divided by 0.0046, we would get the same terminal velocities later. Important to note, our plus c, because x of 0 equals 0, and if you put v equals 0, you take the natural log, so that would also go to 0, and that goes to 0, and you take the natural log of 0.341. You notice these two numbers are equal and opposite, but the natural log of 0.341 is negative. So this would turn into a positive, and we end up with a number in the 1200s. Very which is very, it says that x of 0 would be, 1,200 meters, so almost a mile long. So we find that c equals negative 1,234.17, but that's also accounting for this value right here. So moving forward, actually, because it's a constant, I actually would just take this value that didn't have a variable out, because it would be accounted for in the c value anyways. So ignore this f of x here, that was just how it was in the calculator, but we get that x of v is equal to negative 7.413v minus 594.532 times the natural log of 0.341 minus 0.0046v minus 639.641. Again, I did this first one 2 ways, second way here, just to see if I get the same answer and make sure I was being consistent and was correct. So I got the same thing either way. That was before the plus c, but after the fact I didn't feel like I needed to test that out because it would give me the same answer, because those components are all the same, and then that's the same as up here. But then again, same thing for all. Use u substitution. Pretty much just, again, using the previous. Use substitution, finding the patterns and such. Now that those negatives cancel out, so they end up being positive anyways. And yeah, again, using the plus c, determine the plus c for all, so we start at 0. And really, again, everything here is just a pattern. It's also important to note I, from above, kept everything labeled A, B, C, D, E, and F for later on in the tables that I used to compare values. The next thing was determining the terminal velocity for each thing. So I said it earlier, but sum of forces equals mass times acceleration. At terminal velocity, acceleration equals 0. So right side of the equation goes to 0. So we know that mg has to equal that force of drag. And so, again, pretty much just sub in our mass values, gravitational constant, or just gravity, and then our force for each thing. Again, I'll show you for part A, even though, as you can see, I did the same process for every single, or for all 6 objects. And again, big pattern here, find the terminal velocity of A is equal to 74.135 meters per second. But again, if I sub 74.135 meters per second into there, it would give me, or times 0.0046, that would actually give me 0.341, and we'd have the natural log of 0, which is undefined. So that is not possible, or it's just not applicable there. So what I did to determine the actual total amount of time, I mean, we go over this later on with 50%, 90%, and 99% of the terminal velocity speed. But I had looked at the smallest possible number or within 0.01, or in this case 0.005, to determine how long it would take to fully reach that terminal velocity. And for part A was 7,154.61 meters and 89.3 seconds. For object B, the golf ball, at 80.17 meters per second, or 80.16, it took 68.27 seconds and 40,835.56 meters. For the cylinder in the long form, this is also assuming that it falls perfectly in that direction. That should be an important note and doesn't rotate or flop around in the air. It took 24.5 seconds and 813.74 meters. And for part D, or the cylinder in the circle, so falling long ways, it took 43.55 seconds. And then 1,516.94 meters. For the block blunt, or the big part of it, it took 20.69 seconds, and it takes 483.25 meters to do that, or to reach that. And then for the block in the long way, it took 72.14 seconds, or 5,050.81 meters. And finding, just doing these values for later, literally took copy and paste later on for the tables, but just dividing this by 1/2, or multiplying it by 0.9 or by 0.99 to get our values on the right. And then that leads us to part D, where we're looking for the time to reach each stage. So for the sphere, to reach 50%, again, what I did, you won't see any actual math here, but what I did is just plug the function into the calculator, the time function into my calculator, and then just plug in all of these values here, and then it gives me our time results. So to reach 50% of terminal velocity, it took 5.139 seconds, or it will take. To reach 90%, it takes 17.072 seconds, and to reach 99%, it takes 34.147 seconds. And that is very confusing to look at, because for 50%, you'd expect you're like, wow, it takes 5 seconds to reach halfway. You'd expect it to take 10 seconds with that logic to reach fully terminal velocity. But because then looking at 90%, you see it takes 17 seconds to reach that. It's a fairly big, it takes 12 seconds to go for the next 40%, when it only took 5 seconds to go the original 50%. And then just to go 9% further to 99%, it takes double the time to reach than it takes to reach 90%. But the way that it makes sense to me, as V increases, so as you have velocity going up and your sum of forces is MA, you have mg minus that small 0.0046 V minus a very small number, like 0.006 equals MA. So mg, that stays constant no matter what. As velocity increases, that means that the left side ends up getting smaller. If the left side gets smaller, because this number is getting bigger, or as velocity goes up, the left side of the equation gets smaller as a whole. If the left side gets smaller, then once you divide by the mass, you'll realize that the acceleration is also getting smaller with time. So as v increases, acceleration decreases. So it takes longer to go between stages, or just between speeds. And so it's the same thing here for the golf ball. Reach 50% of its terminal velocity, it takes 5.531 seconds. 90%, 18.37 seconds, and then 99%, it takes 36.693 seconds. So these objects are fairly similar. Their force equations were fairly similar shapes and such, so I'd expect to see the same exact characteristics, and you do see that. It takes about double, and that's a little more than 3 times that. Then for the cylinder in the long ways, for TC here, or for object C, but 50% of terminal velocity is 2.711 seconds, 90%, 8.968 seconds, and then 99% takes 17.456 seconds. So nearly the same, and again, same trends, a little bit more than 3 times that, and then that is about double. And then for object D, the cylinder circle, I should also say we have a percentage, and then what that velocity is, that is what I inputted into the function. And then we have to reach 50% terminal velocity for the cylinder circle, 4.415 seconds, 90%, 14.661 seconds, and 99%, 28.889 seconds. And then for the block blunt, we have 50% of terminal velocity at 1.829 seconds, 90% at 6.079 seconds, and then 99% at 12.124 seconds. Again, this whole left side is from above that I showed, and then it's just what this output on the right is. Then for object F, the block long weighs half of terminal velocity. It took 5.578 seconds, or it will take. Then 90% of terminal velocity will be 18.545 seconds, and then 99% is 37.424 seconds. So, again, very similar trends. That's about double. That's about 3 times that. So, again, 3 times that, and about double. So, not saying that my calculations are totally right. I mean, I don't know if they truly are. Might have integrated wrong, but I'm pretty certain that, it makes sense to me. But actually, I did distance first and then the time one because I was more nervous about the distance one working, because it was a bit more of a complicated integral that, again, wasn't sure if I integrated right, but it all makes sense to me. And I feel like the time and velocity ones go hand in hand. So basically, this is what I explained earlier and where I noticed the trend, and then the time functions confirmed it. So yeah, as velocity goes up, force goes up, so the sum of forces goes towards 0, which means the acceleration goes towards 0. So acceleration gets smaller and smaller and smaller, so it takes longer to go faster, which explains the big jump from 90% to 99%. And you'll even notice from this 99% to what I would put here is, that takes a very, very long time because that acceleration is so tiny. Yeah. But then for part E, for the sphere, or object A, half of terminal velocity took 137.358 meters, 90% takes 874.574 meters, and 99% takes 2,194.58 meters. So you see this humongous jump because at this point it's going 66.7 meters per second, and it takes we already saw how long it's got 7 you take the difference of these, you have 17 seconds at above 66.7 meters per second. So if you just do the simple math there, you end up with quite a big number in the thousands, or above 1,000. So that is a logical jump to me. Yeah, 99%, it takes 2,194.58 meters. That's, you're nearing a mile and a half. Then part B for the golf ball, see the same thing. Half of terminal velocity takes 123.69 meters, 90%, 897.476 meters, and 99% takes 2,309.42 meters. So that actually is interesting, though, because 50% it takes less time to reach, or less distance to reach than the sphere, but it takes more to reach part 90% and 99%. And all the functions are slightly different, so results will vary, but it's just interesting to see things. Then for the long cylinder, so when it's on its side like that, it takes, reach 50% terminal velocity, it takes 29.7925 meters, and 90% takes 215.161 meters, and 99% takes 536.605 meters. And for the cylinder circle, where it's falling again perfectly like that, meaning that the force of drag doesn't change on it and such, to reach 50%, it takes 73.797 meters. 90% of its terminal velocity, it takes 531.921 meters. And to reach 99%, it takes 1,209.54 meters. And for E, the block blunt, which means when it's a square, to reach half of its terminal velocity, it takes 13.705 meters. To reach 90%, it takes 99.202 meters. And to reach 99%, it takes 254.609 meters. And then for a final calculation, for the block long, which is when it's a rectangle, I believe, reach half of terminal velocity, takes 122.528 meters. For 90%, it takes 890.784 meters. To reach 99%, it takes 2,321.4 meters. So, that was a lot. Lots of integrating and then using equations. And then just putting values in after calculating said values. So it's kind of a mouthful, but interesting to see. And so most of our group work or discussion centered around what function to use. Again, we were all a little confused because to us this is what we know from regular physics, and I went ahead and just used these equations from the get-go, but some of our group mates and people we met, or other teams we met with, thought about using this guy because it just makes more sense, but it also complicates things a little bit, that v squared. So, do we get a far more accurate reading because, as you see on the graphs, or as you can tell with the graphs, just depending where you put the intercept, or even, that affects the slope, and also just the parabola tends to follow a bit better than the linear equation, especially because this will keep going up over time versus that straight out. So the further you go, the more variance you're going to get. But yeah, so that's where, a lot of us started getting wonky numbers, either if people try to use this equation for F, for the mg minus F, or people forgot to include the mg part, it would just throw and get negative numbers and such, and so that would be a little confusing, but thankfully we were able to talk it through and find a solution, I believe. And yeah, this is all about finding patterns and such between them to kind of simplify things, and then checking using resources or calculators to make sure that the derivative was correct. Not sure if doing it by hand was the smartest move for everything, but I was trying to be thorough. But yeah, lots of revelations, making sure that the C was done or used so that the values end up being the same. Be happy to go into every integral more in depth, but I believe it would just be redundant. Yeah, very interesting.